This video is sponsored by Brilliant. Hello and welcome to a coding challenge, Quicksort visualization. What you're seeing here are the results of my previous sorting visualization challenge where I did the bubble sort. Now the bubble sort is a really nice sorting algorithm to start with. It's pretty easy to, well, relatively easy to implement with just some for loops, but it's very inefficient, and it's super inefficient because it is an algorithm that takes on average O, the letter O here standing for big O notation, or the order, the magnitude of how long a particular algorithm takes based on how many elements of that algorithm there are. So with an array of n elements, the bubble sort typically takes O n squared. Now the quicksort algorithm is on average a big O n log n algorithm. And maybe at the end I'll come back to unpack why is this. But one of the things I love about the quicksort is its divide and conquer approach that requires recursion. So I've done a lot of things with recursion on this channel before, more in computer graphics or drawing a fractal tree or some other type of recursive pattern. But here we're going to see a recursive function, a function that calls itself. So let me describe and try to diagram out the quicksort algorithm as best as I can before I start implementing the code. So first of all, let's just say we have an array, and I'll just make a really small array right now with just, I don't know, 1, 2, 3, 4, 5 elements in it. 7, 2, 6, 5, 4. All right? So this is my array, and the idea here is I'm going to write some function, and I'm going to call that function quicksort. Now this function is going to expect being passed into it some array. And then it also requires the idea of the quicksort to say, I want to apply this algorithm, the quicksort, to some part of the array. And we're going to recursively subdivide and subdivide and subdivide the array and keep quick sorting different parts of it until the whole thing is sorted. It's like magic. But when we're starting, what's going to get passed in is index 0 and 1, 2, 3, and index 4. So the first time I call quicksort, I'm going to say sort the array from 0 to 4. Now one thing though that I'm going to want to check, the whole point, this is going to be a recursive algorithm. So the main thing is start has to be before end. Right? So the array is going to recursively get subdivided and subdivided. So at some point, if start and end are in the same spot, that's when I'm done. So that's going to be the first step here. If I think I could just say if start is greater than or equal to end, something like return. That's going to get me out of it. All right, but here's the key. The idea of the quicksort is basically to say, I want to do a step which is called partition. And I need to pick some part of the array that is called a pivot point. So I'm going to make a nice, sort of easy way to pick that is always just have the pivot be the end spot. And the idea is I want to take everything that is less than the pivot value and put it on one side of the array and everything that is greater on the other side of the array. So if I were to do that with this, I could just visually see I'm going to get a 2. A 2 is the only thing less than the 4. And then the 4 is going to go here, and then the other things are going to be on the other side, like 7, 6, 5. So they don't have to be sorted 7, 6, 5. So this is what I'm doing. I'm taking this pivot, putting it in essentially the center, so to speak, the middle of the array, and then everything that's less goes on one side, everything that's more goes on the other side. So this partition function, where I give it the array, the start, I think I still give it the start and the end, and then also the pivot, right? What I then want this function to return is an index value, the index value of where the pivot ended up. And actually, I think I don't have to do this because I can always use the pivot point as the end. So I'll figure that out as I code it, but stay with me here. So in this case, what this actually ends up returning is the index 1. Because what I then can do is I can say, hey, now that I got that index of where that pivot is, I want to just quicksort. So I'm going to recursively call quicksort on that array from start to that index -1 And also quicksort, this is dividing and conquering from that array from index +1 to end. So basically, these are the steps. We start with the array, we pick an arbitrary pivot, we put everything on one side or the other, and then we figure out where that pivot ended up, and then we just quicksort both sides, and those will put something. So this is done because it only has one element left. So start and end are in the same, so it will return. This one will pick 5 as the pivot, and then it will become 5, 7, 6 because everything's on one side. 7 and 6 are bigger than 5, so this is then done, and then this then gets quicksorted. 6 becomes the pivot, so 7 goes on the side, and we're left with 2, 4, 5, 6, 7. Whew. So maybe my diagramming and explaining isn't the greatest, and we also have to write the partition function. I mean, that's the whole, how do we do this partitioning? But let's start, I think now let's go over to the code and start writing it in our code. All right, so here I am with my code. I'm going to remove the bubble sort, and I'm just going to leave the drawing of the array, and I'll take out this frame rate 5 thing for right now. Actually, I'll leave that in there. And now if I go and refresh, we should see there it is. Every time I refresh, I'm looking at the array of random values unsorted. So the first thing I want to do is just see, can I get the sorting to work? And then I'll figure out visualizing it is, I guess, the interesting part here in some ways, but let's get it to work first. So the idea, right, we need to write a function called quicksort. It's going to receive an array and a start and an end. And I said if start is greater than or equal to end, then just return, like jump out of there. Otherwise, I need to get this pivot index where I'm going to partition the array from start to end. So I want to call this partition function. I mean, this is really, ironically, I haven't explained the partition. That's really where the algorithm is happening. But I want to run partition, and I definitely don't need to pass in an extra argument because I'm always going to use the endpoint as that pivot, so that's fine. And an index is going to come back, and then what I want to do is say quicksort that array from start to index -1, and quicksort that array from index +1 to end. So this is the basic idea of the recursive algorithm: divide and conquer. And I'm going to call the array. I'm going to call it first with values and go from 0 to values.length. Now, do I want to say values.length -1? Probably. So I'll figure that out as we go. Because the last element is not the length, it's the length -1. Okay, so now, of course, we really have to, I just realized. So this is the idea. Now we have to figure out partition. Let's look at the partition function. This is really where the magic happens. This is the core algorithm. So once again, let's make up an array with just 5 elements in it. Let's say 9, 3, 5, 6, 4. Let me move, just to make things more even, let me put the 4 here and make the 5 here, okay? Just to, I think an example will work out better this way. Obviously, any order, the sorting algorithm will work. So the idea of the partition function is when you call the function, you give it the array, this is the array, you give it a start and an end. So in this case, the start is going to be 0. This is the start. And the end is going to be in position 0, 1, 2, 3, 4, in index 4. So this is the first time I call partition. It's going to get called on this array. Now what I need is a pivot value. I need a pivot index and a pivot value. The pivot index, we'll talk about that in a second. The pivot value, I could pick anything in here, but it's most convenient to just pick the last one. So I'm going to say the pivot equals 5. And the idea of what I want to do is I want to put everything, I want to rearrange this array so that everything that's less than 5, like the 3 and the 4, are on the left side, and everything that's greater than 5, like the 9 and the 6, are on the right side, and then 5 will be smack in the middle. Now, it won't always work out that the pivot ends up in the middle, because everything could be bigger in it, and the pivot would end up here, and there'd be nothing on the left side. But I made a little nice example so that it works out cleanly. Okay, so how do we do this? So first, we need to iterate through every element of the array I equals 0 all the way up to the end minus 1. So we need to check every single element of the array, and we need to compare every single element of the array against 5. I also need to keep track of the pivot index, because as I go through this process, I'm going to need to find once I'm done, the 5 is going to stay here the whole time. I need to quickly put 5 back into where it's supposed to go. So that I'm going to just call index. It's really the pivot index. So this is the pivot value. This is the pivot index. That's going to start at 0, and I'm going to put a star here for that it's starting here. So I is now 0. 9. Is 9 greater than 5? Yeah, it's greater than 5. I know that. That means I do nothing. So I'm checking if array index I is, I'm checking if it's less than, actually. It's not less than. If it's less than the pivot value. So if it's not less than the pivot value, I don't do anything. Okay. Now I goes up, so I is now here. Is 3 less than 5? Aha, it is. So guess what I do? I now swap I and wherever the pivot index is. Remember, the pivot index was at 0. So 3 and 9 are going to swap. So 3 goes here and 9 goes here. And then guess what I do? I move that pivot index. So the pivot index is now here, and then I move I, and I'm checking 4. Is 4 less than 5? It is. So I do this again. Swap I and the pivot index. So 4 goes here, 9 goes here, and the pivot index goes up. So the pivot index is here. Then I go here for I. This is the last one I need to check. Is I less than 5? No, do nothing. So I'm done. This is the array. 3, 4, 9, 6, 5. Huh? Well, you can see that 3 and 4 are here, they're less than 5. 9 and 6 in here, they're greater than 5. Guess what? The reason why I need that pivot index is the last thing that I do is I swap the pivot index with end. So now I can just take what was on the end, put it here, put the 9 here, and I have this algorithm has successfully put everything less than that pivot value on one side of the array and everything greater on the other side of the array. And the really nice thing about this quicksort algorithm is I don't really have to use additional memory. I didn't have to make a copy of the array to move things around. And the merge sort, if I ever do the merge sort, you see you need to start like having extra copies of the array. So that's one nice thing about the quicksort. So the chat has given me some good feedback that the way I used I and index is a little bit awkward. I think what I might actually do is name this pivot value in when I write the code, and I'll name this pivot index. It's a really, that's being very long-winded, but I think it'll make it more clear. So let's go write that code now. So if I come back to the code, all I need to do is write the partition function. So I'm going to write a function called partition. It's going to receive an array and a start and an end. And then what did I say I want to do? I need to have a pivot index, which is going to start at 0. I need to have a pivot value, which is going to be the array at end. And then I need to iterate from I equals 0 to I is less than end minus 1, I plus plus. And now I'm checking if the array I is less than the pivot value, then what I want to do is swap. I already have a swap function. A swap function just takes an array and 2 indices and says whatever was in A, store it, because you're going to want to put B in A, and then what you saved in A, put it in B. So swap array A and swap array B. So I already have that function. So I can say swap I and pivot index, and then pivot index plus plus. And then once I finish that loop, I just need to swap pivot index and end. Array, pivot index, and end. Wow, that was quick to write. Is there any chance I got that right? All right, let's run the code. Okay, we got an error. Maximum call stack size exceeded. So this is a very common error, which is that if you recursively call stuff way too much, things blow up and you've exceeded things. So let's take a look at the code. Oh, of course. This is not where the pivot index starts. You don't always go, remember, I just said 0 because I was thinking about doing it over the whole array. But the whole point of this is you're starting at start. Start isn't always 0. That was a nice little mistake there. So this should be start. Is that the only error I have? Let's see. No. So there's some other errors. Let's see. Oh! Yikes. I forgot. So I forgot that my swap function, the way that I wrote it, there's no global array. You have to tell it what array you want to swap the values in. So that needs to be explicitly added as an argument there. Was that the only mistake? Oh, you know what? Here's my other error. I know that this is end, so I want my loop to go from 0 to n minus 1, but I'm using just the less than in my for statement. So I don't need n minus 1. I need just end. So many errors still. Oh, return the index value. Okay, I forgot the whole central idea of this. The whole central idea of this is that the partition function returns back where that pivot index is so that you can divide and conquer and do the right and left halves. Look at this. I don't return that anywhere. I just finish and I'm like, I'm done. Here's an undefined pivot index. I need to actually say return pivot index. What an important key line of code. And I'm getting closer, everybody. And another mistake. Oh, I've made so many mistakes. I'm the worst. This is also from start, right? I'm so focused on thinking about the beginning first step, where you go from the beginning to the end of the array, but the whole idea of this partition function is that you're anywhere in the array. So this goes also from start to end. There we go. So now there's my sorted array. You can see that the quicksort actually works. All right. Whoa, now that we're about 3 hours into this video, I should visualize it. It's really tricky to visualize something that's happening recursively because it's not happening in an obvious first step, second step, third step. So let me just draw it at the first step, draw it at the second step. So this is, now what happens? What do I mean here? What if I make this quicksort function async? Weird, right? Let's just add that async keyword there. Same deal. Interesting. Let me also make this partition function async. And what's important there, I forgot something really important. So I'm surprised that even worked. If I'm making the quicksort function async, I'm going to want to await quicksort, both calls to quicksort. I want to be able, those are happening asynchronously, and I want to await them because I want everything to happen in the correct order. I also want my partition function to happen asynchronously, so I'm going to put await in front of that. Now, if the async and await keywords are new to you, I will refer you to some other videos where I go through those in more detail. But this is what I'm basically allowing this to happen is that this function quicksort can be called, and then draw is going to go on. The thing is, the sorting is so fast. You can see it. There's like a little blip there, right? That little blip where you see it, but it sorts it so fast. What this means is if I could just make something happen, and let's make swap asynchronous, and let's await it everywhere. If I could just add a little delay somewhere, I could force the actual sorting algorithm to slow down, but draw would still be animating. So there are other places where swap happens there, swap and swap. So how do I make this slow down? Well, I could use set timeout, but what I want is I want a function that's like delay that I could use await. And I'm going to have to write my own function for doing that. So on Stack Overflow, I found this nice piece of code that basically takes set timeout, the set timeout JavaScript function, which has a callback, which is callback based and resolves a promise when set timeout finishes. And this is the equivalent of an asynchronous sleep function. It's kind of like await and don't do anything, wait and don't do anything for this amount of time. So I'm going to bring this function into my code. I'm just going to put it here on the bottom. And now I can say await sleep 1000. What that means is, hey, before you swap, just wait a full second and let's see what happens. I think my sleeping might be too long, right? A full second. So let's just bring that down to 10. And we can see, there we go. So one thing that I noticed, and that the chat really just helped me out with, is that because I am using await here with each separate quicksort step, the actual sorting visualization is kind of, the recursion is not happening simultaneously. It's doing one half, then the other half, then one half, then one half, then one, step by step, which is kind of nice for visualizing it. And that's really, really fast. I'm going to put in a sleep time of like 25 milliseconds. And you can sort of see how this is happening little bit by bit by bit by bit, and then it's done. However, I forgot that I could use promise.all. So I could await promise.all, both of these calls to quicksort at the same time. So if I do that, and just paste this one up here, this is getting to be pretty goofy advanced JavaScript stuff. But this is basically saying, hey, you can go do both of these simultaneously. I'm just going to wait for both of them to finish. And this, in theory, can you visually see the difference of that? I don't know how obvious that is to you. It'll be much more obvious if I did something like color the various pivot points. Let's see if I can do that. And I have a really goofy idea of how to do that, which I think is probably terrible. But this is the last thing I'm going to do before putting this aside. So what if I have an array, because there's multiple pivot points that are being tracked. What if I have an array called pivots? And any time, should I draw the pivots as they're moving, or just draw them as they're, let me draw them as they're moving. I'm going to do overkill. This might not be the classic way of visualizing this, but basically, whenever I get a pivot index, I want to add it to this array. I really want to use just like a lookup table. Actually, that's what I should use. Aha. So what I want is an array. I really want an array of true and false. Like, what's the state? Let me do this. This is much better. States. So as I'm creating my values, the states of every single spot is going to be -1. So what the current status of a particular element of the array is how I'll choose to color it. So in the case of whenever I get a pivot index, I'm going to say states pivot index equals 0. So -1 means nothing, 0 means it's a pivot index. So this is a little bit ridiculous, but let me just bear with me. And now I'm going to say if states index equals 0, which is meant for pivot index, make it red. Otherwise, make it white. Oh, this is going to be good. I think this is going to get us what we want. So you can see anytime there's a pivot index, it's set it to red. Now I'm not unsending it. I'm not unsetting it. So one thing that I could do then now is I could say here, if I'm moving the pivot index, right before I move it, let's set that back to -1, and then set it again to 0. So now you can see the pivot indexes are moving. Now again, I'm not unsetting it when it's done, which is sort of a problem. So I suppose if I wanted to do that, I could also say states index. This is where it's like finished. There you go. So it's happening very, very fast, but that's the pivot stuff moving around. I don't know if I'm doing this in the right way, but it also might be interesting to, as I am sorting between start and end, any given active partition, like I could do I equals start, I is less than end, I plus plus. I could say states index I equals 2, I don't remember, or 1. And then I could also, at the end, after I'm done, set it back to -1. So I could say that if states index I equals 1, then maybe make it blue. Again, I'm not being too thoughtful about my color schemes, but let's see what happens here. I don't know. That's kind of like what's going on. Let's give ourselves a much bigger space to work with. Let's actually make, let's make this the full window, window height. Let's make the width of each one just 5. And then I think I probably want to say no stroke here. Because if they're thinner, that might mess up how it looks. And let's make 100 milliseconds sleep time between each swap. And let's go enter full screen. And I'm going to let you enjoy this. I'm going to step aside. All right, I need to change the colors. Those were no good. And then there's another mistake. If I don't want to, if I is pivot index, so as long as if I is not equal to pivot index, I don't want to undo the coloring of it being currently sorted. All right, thank you to the chat who offered these colors as suggestions. I'm going to just leave it at that. I'm going to make the lines a little thicker. Let's leave the width at 10. Let's make it run a little bit faster. So I'm going to double the speed. All right, I've got the code in the state that I want. I'm going to play you out and let you enjoy this last visualization of the Quicksort. And please make a nicer version of this. Add sound, add better colors, do all sorts of stuff. Here I'm going to hit refresh. Thank you for watching this coding challenge, visualizing the Quicksort algorithm. You might notice that the version that I made, it looks okay. I did fine. It might look different than some others that you've seen. In particular, there's a very popular video on YouTube called 15 sorting algorithms in 6 minutes. It has like 6 million views as of the time of this recording. And the Quicksort visualization looks kind of different. And that's because there are actually multiple ways to do that partition step, that partition function that takes the values of the array and puts a bunch that are bigger on one side and a bunch that are smaller on the other side. And there are two techniques. There's the Lomuto partition scheme, which is attributed to Nico Lomuto. And that is the one that I'm using, where you pick that pivot and then you start at the beginning of the array and check everything to figure out where that pivot should go, basically, where it should get moved to. There's another one called the Hoare partition scheme, which is described by C.A.R. Hoare. You can find more about this on the Quicksort Wikipedia page. That starts with index values at both ends of the array and has them walk towards the middle, swapping elements. And that's, in a way, that's one that you should try. So if you want to go look that up, look that algorithm up and try changing my code but still visualizing it, that might be something exciting to try. And maybe you have other ideas for your own version, for your own way of visualizing this Quicksort algorithm, using color, using sound, using shapes and design in a different way. You don't have to be so literal about the array as just a bunch of bars going horizontally across the canvas. Please share with me your version at thecodingtrain.com. And I'll put a link in this video's description. And there you'll find pages for all of my coding challenges. Now, one of the things I really struggle with these days is how do I think of a new idea for next week's coding challenge? And I get a lot of great suggestions from the audience. I get ideas from my students here at NYU, but I'm excited to tell you about the sponsor of this video, where is a treasure trove of more ideas for coding challenges, and that's Brilliant.org. Brilliant has a wide range of content, math and science and computer science. They have daily puzzles, they have courses. I've actually been enjoying looking at their daily puzzles and trying to solve them with JavaScript. And that's been a sort of fun way for me to try to learn something new and also practice a little more coding. And in fact, probably most relevant would be the courses on Brilliant that are computer science fundamentals, intro to algorithms and recursion. You'll see lots of things from my coding challenges in that course, as well as the computer science algorithms course, where in fact there's a whole module on sorting. And I reviewed that Quicksort, the module on Quicksort, while preparing to do this coding challenge. To sign up, go to brilliant.org/codingtrain. That'll let them know that you found it from this video. And also, as a special offer to Coding Train viewers, the first 200 people to do that will get 20% off their premium service. Thanks for watching. I hope to see you in future coding challenges, and I can't wait to see what kinds of quicksort visualizations you make.